So good morning, everybody, and thank you, Brian, for the introduction. My name is Kristian Börger. I'm from Aachen, Germany. I'm a civil engineer with a structural background, but today I'd like to talk to you about a fire scenario assessment. I would like to give you a brief insight into fire scenario assessment, but before I would go deeper into the process of selecting fire scenarios, I'm going to tell you about performance-based design in Germany as in general, its application and daily practice, and I'm going to talk a bit about the recent standardization work on DIN 18009 framework. I will close my presentation with a short application example. So in the individual German federal states, there are independent building codes, so we have a total of 16 building regulations for assembly, industrial buildings, garage, shop and mall, and electrical facilities, for example. But in Germany, performance-based design methods are not explicitly embedded into the building codes. So according to this, major knowledge about material and product performance is closely linked to a prescriptive design approach. This approach has provided a substantial improvement into fire assessment, but however the increasing individuality and complexity of modern buildings may conflict with these requirements. So performance-based design has established in Germany as well. So up to now, the directive for industrial building is the only performance-based design approach in Germany right now. So, but usually the fire protection requirements in line with building regulations are by selecting verified structural elements and technical firefighting measurements, for example. So due to the lack of calculation methods and performance criteria or acceptance criteria, the German Fire Protection Association decided to issue a guideline to harmonize disjointed approaches and assumptions and to avoid erroneous into the from the application of engineering methods. So in the year 2008, the DIN Working Committee Brandschutzingenieurswesen, which is fire safety engineering, in English started its work to standardize fire safety engineering methods in Germany. As a result of this, the first issue of DIN 18009 Part 1 has been released in September of this year. So this is intended to be a basic document which describes the necessary terms and definitions related to the design process and the methodologies in fire safety engineering. Part 2 of the DIN 18009 is it covers evacuation modeling and life safety assessment in case of fire. And Part 3 is about the identification and selection of design fire scenarios with a special focus on the selection of fire models like CFD models, ozone models, and so on. Part 2 has been issued as a draft status, but Part 3 is actually in progress. So a performance-based design approach in general may be required if the compliance with fire safety goals according to building regulations law is not possible by fulfilling prescriptive requirements. So if the evidence should be provided by a fire safety simulation in terms of a performance-based design, there have to be performance criteria. So the guideline to fire protection engineering in Germany gives examples of how this can be done, of how we can derive functional requirements from the fire safety goals, which in turn can be quantified by performance criteria for further consideration. So for example, if our fire safety goal is preventing the spread of fire and smoke, the functional requirement derived therefrom is the fulfillment of material demands and on petitioning elements, and our performance criteria derived from this maybe can be a maximum temperature or heat radiation to the respective component. So the evidence of performance-based design is usually provided by comparing the defined performance criteria on the resistance side with the calculated results on the action side. So the influencing variables must be selected on sufficiently conservative assumptions. Uncertainties at this point have to be taken into account by calculating maybe partial safety factors, or they can be these partial factors can be taken from appropriate standards or maybe calculated within a safety concept. So I'll now turn a bit more in detail about the principles of the description of fire scenarios. So in general terms, fire scenario describes the boundary conditions as well as a sequence of all influences that influence the fire development. So it should be noted that the possible key events have to be taken in a temporal context in order to avoid the definition of unrealistic scenarios. So a basic procedure for this selection of fire scenarios is given in DIN 18009 part 1. So we have the steps, at first the identification of fire scenarios based on the building utilization. Then we have the identification of critical sites for the fire, the determination of the effects of factors that influence the fire, the determination of the influence of the building users, what may influence a fire. Then we have the assessment of the fire risk. Before we have the assessment of the fire losses, of course. And last we have the selection and documentation of the fire scenarios. I would now like to take a closer look on these above steps by giving an example of how a workflow may work. So at first, all the fire safety goals and the performance criteria have to be defined to recognize possible hazards. So with regard to the performance criteria, those scenarios have to be identified with common causes of fire as well as scenarios which result in a serious economic and personal damage. For the individual scenarios, different places, different sites for the fire to occur have to be considered. So for example, to verify a successful, from these sites, those with the worst impact on the fire safety goal have to be taken into account. So for example, if you want to verify that a safe escape of a building is possible, you have to take into account the scenarios within the escape routes, or maybe scenarios which make escape routes impassable. So if all these variables have been collected within a qualitative analysis, we now have to take a closer look on the events that may occur during the fire development. So the fire development can be influenced by structural as well as geometrical circumstances. So we have to determine a burning area. This can be done by having a closer look on the arrangement maybe of room closing components so that we can reduce the fire to one area. Also very important is getting information about the ventilation conditions, maybe by having a look at the windows, the doors, and the smoke extraction respective their opening criteria. And in a similar way, we can define the influence of technical firefighting measures like automatic extinguishing systems that maybe influence the heat release rate we want to calculate. So on the other hand, we have to determine the influence by the building users on the fire development. This can, so from the type of usage of the building, you usually can estimate some factors like the probability of causing a fire maybe by the users, or the reaction to the building users by detecting a fire by themselves or by getting alarmed, and you also can predict the probability of a successful extinguishing attempt maybe. So since some of the factors are very are subject to very large scatter, they have to be taken into account by appropriate safety factors also. But you also can maybe develop event trees like this to consider all thinkable scenarios. So the next step, the possible fire scenarios and the probabilities of occurrence for the scenarios have to be selected, and they must be linked with the estimated fire losses. The fire losses may be estimated by the definition of, or the estimation of personal damage or maybe material damage. If you link these probabilities of occurrence and the fire losses, you get the fire risk. It's defined as the product of both. But it should be clear that the identification and the definition of the design fire scenarios operates in a mutual way, in a mutual interaction with the subsequent fire simulation, so that the entire process should be regarded as an iterative procedure. So maybe if you want to take into account the effect of an automatic fire extinguishing system, you first have to define a fire in order to maybe calculate the triggering time of the system. So the scenario-based design may be explained best on the shown graph. It's taken from DIN 18009 part 1. So for a defined assessment period, which usually is the service lifetime of the building, all possible scenarios have to be collected with their respective risk. So in the first step, the individual scenarios can be grouped into maybe bagatelle scenarios that have a negligible effect regarding the respective fire safety goal. So the probability of occurrence for these scenarios may be of rather subordinate importance. Then there are worst case scenarios, those ones, which may result in high fire losses, but are also quite unlikely to occur. So we don't have to consider them either. And then we have scenarios with a high risk, which are also not important to have a look at because they are unacceptable, which means they have to be eliminated within a redesign of the fire protection concept. So the remaining scenarios now form the relevant scenarios, from which significant scenarios have to be grouped into clusters. This may be done by acceptance criteria. And from the respective clusters, now design fire scenarios have to be determined. You can take one scenario of the respective cluster, or maybe you can develop a new scenario which is representative for the cluster. So before we go more into detail regarding fire modeling, we again need to be in mind about the difference between the fire scenarios and the design fire. So the fire scenario, as I already said, describes the circumstances and the sequence of all influences during the fire, whereas the design fire is a quantitative description of the fire within this scenario. So for many fire protection verifications, square increase in heat release with a constant fully developed phase and a linear decay stage is a suitable approach. These models are usually described by maybe a maximum burning surface, a fire load density, a spread rate, and so on. So additionally we have to take into account regarding the fire safety goal to be achieved, maybe a detailed combustion reaction in order to take into account of combustible products or soot. So the following application example should give you an insight in the process of the selection of fire scenarios. It has been decided not to do a comprehensive risk analysis because it's not suitable for this rather simple case. So the example shows a 3-story building in a solid construction. You have a lobby, a restaurant, and office units at the ground floor, and the first and the second floor, which are rather similar in construction, have offices and meeting rooms. And what is important for the next step is to consider the roof structure of the building, which is designed as a unprotected steel frame, and the roof structure formed at this point a bracing element of the overall structure of the building. So for the considered building, the following fire safety goals can be derived from the German Model Building Code. We have prevent the fire from starting, prevent the spread of fire and smoke, enabling of escape and rescue, and enabling effective firefighting measures. So since some of these stated objectives cannot be achieved just by fulfilling prescriptive requirements, an equivalent level of safety has to be ensured by a performance-based design. So let's have a closer look to the last of the stated objectives. So in order to enable an effective firefighting, we have to ensure a sufficient stability of the load-bearing structure, so at least 90 minutes to isofire. So this cannot be guaranteed by the structure without further evidence. Now the evidence should be provided by a structural analysis in fire, depending on, based on natural fire according to Eurocode 1. So in Germany, the proof of an adequate stability in case of fire is provided if a failure of the structure does not occur during the entire process of the fire, including the decay stage. So to identify possible sources of ignition for the building, the utilization of the building is of major importance. So in this case, we could identify maybe defective electrical equipment, computers or kitchen equipment as possible sources of ignition. So essentially all of the individual office units as well as the restaurant and the lobby have to be considered as potential areas for a fire. But with regard to the fire safety goal to be achieved, only those scenarios must be considered which result in a high thermal load on the load-bearing structure. So the closer examination in this case can be reduced to a fire event on one of the office units on the second floor. So on this floor, a total of 3 areas that are formed by room closing components can be considered as potential places for a fire. So since the probability of occurrence is comparable for 3 office units, the risk analysis at this point is limited to selecting a fire event with the greatest impact, which obviously is a fire in the greatest unit, taking into account also the ventilation conditions. So taking into account uncertainties and failure probabilities of human and technical nature is covered by the national annex of Eurocode 1, by the safety concept of the national annex. So for an office utilization, the annual probability of occurrence for an initial fire can be determined or assumed to 6.2 by 10 to the power of -3. So this value can be either taken from tables or maybe can be calculated depending on the building or the unit's area. So furthermore, the probability of failure for firefighting measures as well as firefighting measures by the user, by the fire brigade or by maybe an existing extinguishing system could be considered with the shown values. So we can we get an entire probability of occurrence for destructive fire in the utilization unit. So in conjunction then with the permissible failure probability, we get a conditional failure probability as well as a linked reliability index, which can be calculated using the inverse function of the standard normal distribution at this point. So by using different variation coefficients, we now can calculate the partial safety factors for the heat release rate, which is 0.98 fixed, and for the fire load density, which is 0.981. So finally, taking into account the partial safety factors, we can calculate the design values for the fire load density as well as the heat release rate. These input parameters we need to calculate the design values are given as 90% quantile in Eurocode 1, which means they will not be exceeded by an actual fire with a probability of 90%. So in consideration of a spread rate, I think it was 300 seconds up to reaching 1 megawatt in this case, and maybe taking into account flashover criteria, we now can precisely describe our heat release rate curve for the further consideration. But at this point, I'd like to set aside the subsequent structural analysis, because this example was aimed to show the way how the fire scenarios should be selected. So I will now close my presentation with a short outlook and conclusion. So the recently published part 1 of DIN 1809 already describes the fundamentals of selecting design fire scenarios, but especially when it comes to the point where we have to select the relevant scenarios from the totality of possible scenarios, there are some values missing. Maybe we have missing acceptance criteria which line the border for what scenarios do we have to select and what we don't have to select. So for similar reasons, the application of performance-based design methods in Germany is quite different at some points, because the decision whether a fire safety goal is provided by a computational evidence is still with the proving authority. So maybe if you want to do a structural analysis in case of fire using a natural fire, this always is a deviation from building regulations law. So at this point, it would be desirable to get an equivalence of a computational evidence with the prescriptive requirements from building regulations law. So thank you for your attention.
We have time for a question if there's any here. Yeah.
DIN standards in Germany are elaborated by an like privity, or let's say an aggregation of interests. So they are highly controversial. You told us that for the right fires, to choose the right fire scenario, you have to link consequences and frequency. But in Germany, there are absolutely no statistics about fires. So how does this get together? And this is one of the biggest points in Germany at the moment. So
yeah, it's exactly what I said last. There are acceptance criteria missing to say what scenarios have to be considered and what scenarios don't have to be considered. That's exactly the point.
Because this paper gives us lots of data where nobody really knows where these numbers come from.
Yes.